Hello and welcome back to Calero Academy. Today we're going to be looking at how to solve the last two approaches to finding the volume of a cone. Okay, in the last video I promised you that these two approaches would be very similar, and that is quite true. The first approach, let's write out V, uses the so-called double integral, and it says that the volume of any solid is equal to the integral from a to b, say, of the integral from c to d of f of x and y with respect to y and x. Now, what this really means is that let f of x and y be a surface. Then find everything under this surface from along the y-axis from c to d and along the x-axis from a to b. So it's really just saying, suppose we have a surface here. Suppose a to b is from here, say, to here. That would cut off everything but this. And say that the c to d was from here to here. And so this would leave everything under this, going all the way down to the xy plane. Okay, so let's border that guy off away from our normal work over here. And now, two things that we're going to learn anew or relearn for this Calero is two new coordinate systems. The first one is called polar coordinates, and what it does, instead of writing in the normal x, y axes, instead of writing a point over here, say has a, b for its x and y coordinates, instead write how far it is away from the origin, call that c, and what angle theta does it make with the x-axis. And that is how you do polar coordinates. Very simple. The other thing that we'll need to learn for this lesson is cylindrical coordinates. So, cylindrical coordinates is how to identify points in the 3D in space. And so, the way you do it is that you define where points are on the x and y axis by the normal polar coordinates. But then, for the z-axis, to tell you how to call it high it is, you just do the normal z-axis. So it's just, you can imagine it as the child of a Cartesian coordinate system and the polar coordinates. Okay, so it turns out that to find the volume in terms of polar coordinates, it's equal to the integral from 0, from phi, say, to theta, some theta, of the integral from a to b of f of x and y times cap r with respect to cap r and theta. Not the same theta as this one. I made a mistake. I shouldn't have used theta. So, the reason that... So this is how you do it in polar coordinates, a volume. The reason we have a cap r over here is because it turns out that dy dx is not equal to d cap r d theta. Turns out that it's actually equal to cap r d theta. So that's how we do it. And remember to always put your f of x and y not in rectangular coordinates, but to change it all over into polar coordinates. There are lots of textbooks on this thing, and mathematicians really love polar coordinates, so you will not have trouble finding it if you want to find out more information about it. Okay, so let's think of our cone. This is our x-axis, y-axis, and z-axis. So, we'll put our cone, we'll have it start at the origin, and we will imagine it going up like this. So it turns out that the function for a cone, this is kind of a bad z, the function for a cone is z is equal to f of x, y, and y, which is equal to h on r times the root of x squared plus y squared. Now, in polar coordinates, cap r is equal to the root of x squared plus y squared. So as you can see, it would be much easier for us if we put this into polar coordinates. If we rewrite this function in polar coordinates, it's equal to h1r times cap r. H and r determines, for example, if you cut open the cone perpendicularly at some height h, what is going to be the radius of the circle at that point? So h and r will tell us how open it is. So this is going to be the formula for our general cone. Okay. So we have our f of x and y. So we can now write our volume. However, let's not make a mistake that's similar to what we almost did in the third approach in our last video. If you might remember that we almost found everything else besides the actual cone. If you imagine the cylinder, our cone in a cylinder, if we were to just find the volume of this function, we'd be finding everything but the cone. We'd be finding everything under this, but not under this. So the way to counter this effect is just to write the volume of the cylinder, which we know to be pi r squared h, subtracting the integral from blah 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 if we plug in this f of x and y into the volume. So our real volume of our cylinder is going to be equal to pi r squared h, bad r, minus the integral from 0 to 2 pi. And now let me explain this. The reason we have 0 to 2 pi is that we're going to revolve. Okay, I'll explain actually after I explain this integral. So the integral from 0 to 2 pi of the integral from 0 to r of our h of r times cap r times d cap with respect to cap r and theta. Okay. So, the reason that we're integrating it from 0 to 2 pi, first, the reason we're integrating it from 0 to r is that you can imagine that we're just adding up a lot of growing lines up to a certain point. The reason we're integrating from 0 to 2 pi is that we want to revolve this little guy, revolve these lines to get a lot of circles. And so all we're really doing is adding up a lot of circles. In fact, actually what we're really doing is we're actually finding the volume of everything here. But that when we subtract this from that, we are going to be finding an infinite sum of all these little circles in there. Okay. So, let us now do some integration. This is going to be equal to pi r squared h minus the integral from 0 to 2 pi of, we can take h and r out, h and r of r cubed on 3 with respect from 0 to r d theta. And the reason we're doing this is that the Fubini's theorem tells us that when we're integrating a double integral, we can just imagine that the outer integral doesn't exist. So we can just put it on the outside and solve the inner integral. And now, so our volume is equal to pi r squared h minus, now, and by the way, this is going to be equal to pi r squared h minus the integral from 0 to 2 pi of h r squared on 3 d theta. So just simplifying that. Okay, so now the integral of this little guy is, we can take everything out, and we'll have h r squared 3 times the integral of 1 with respect to theta, which is going to be theta, from 0 to 2 pi, which is equal to pi r squared h minus 2/3 pi r squared h, which is equal to something that we all know very well, 1/3 pi r squared h. And I squashed it a bit here, shouldn't have done that. Okay. And so, that is the fourth approach. My hand is blocking the light, sorry about that. Okay, now, let's move up a bit. And our fifth and final approach is going to deal with something very, very nice. It's going to use cylindrical coordinates, and it is going to be using triple integrals. And volume in triple integrals is going to be equal to the integral from a to b, the integral from c to d, of the integral from e to f, of, drumroll please, 1, with respect to z, y, and x. And that is clearly going to be the most beautiful approach in these two videos. Okay, so if we want to put this in cylindrical coordinates, we have to write, similar to the fourth approach, we had to write, instead of d cap r d theta, we had to write cap r d theta. So similarly, this is going to be equal to, in cylindrical coordinates, the integral from, say, what is it? Okay, alpha to beta of the integral from, say, a to b of the integral from c to d. Remember, these are not going to be equal to that. Let's just call them a2, b2, c2, d2, just to separate from these guys. Of cap r dz d cap r d theta, because dz dy dx is not equal to dz d cap r d theta. Okay. Now, if we refer back to our cone for a minute, all we need to do to find the volume of our cone is just to find what the limits of our integration is. So, if we think of it, the volume of a cone is really going to just be the integral from 0 to 2 pi of the integral from 0 to r of the integral from cap r on tan alpha to h. And the reason for this is, what we're doing is we're first integrating from, if we look at it here, we're integrating from cap h. Okay, so look, in a right triangle with height cap h and leg cap r, and it's a right triangle, tan of alpha, where alpha is equal to, where alpha is here, will equal to cap r on cap h. And of course, since tan alpha is constant, it's also equal to r on h. We met that little trick in our first video. Therefore, this is going to be just the integral of cap r dz d cap r d theta. Okay, and the reason it's from cap r over tan theta is that cap r on tan theta is going to be equal to cap h. And so we're integrating from cap h all the way to our proper h, and then we're integrating that from 0 to r, and then we're spinning that around to create r infinite circles. And I think you can, as a little exercise for our Calero students, so we'll leave this to you to actually prove that it's 1/3 pi squared h. But in the end, after integrating 3 times, we will get that the volume is equal to pi r squared h times 1/3. And thank you for watching this Calero Academy video. We hope you had a very good time watching it. If you found any errors, if you want us to make a video or something, as usual, put it in the comments. So thank you for watching this Calero Academy video,